Okay, so hello everyone. It's a welcome to the 8th edition of this talk series. It's a pleasure to have Peter Schrammel here with us today. Peter is an assistant professor of computer science at the University of Sussex in Brighton, UK. And he's also CTO of a company that he has co-founded along with Daniel Kroenig. The company is called DiffBlue, and I believe they use AI to change the way software is developed. Hopefully, Peter will tell us a little bit about that also today. Yeah. So with that, over to you, Peter.
Good. Thank you. Yeah. Thanks for the invitation, Maduka. It's a pleasure to be invited here. So this work is about parallel bug finding in concurrent programs using reduced interleaving instances. So this is a collaboration with colleagues from Southampton and South Africa and Italy. So yeah, common knowledge is that concurrency makes bug finding harder because there is a state space explosion due to a large number of interleavings. So if you look at executions of two threads here, they can follow many different ways, like this one or this one, which increases the state space and makes verification of such programs much harder. And in particular, with modern hardware, with relaxed memory models, there is even more concurrency on a very low level. So, yeah, so this is expected to make it more difficult to verify such programs. On the other hand, concurrency should also make it easier because you can exploit concurrent computations to perform the verification tasks by, for example, splitting them into smaller tasks that are easy to solve and massively parallelize this to solve the verification problem. So you could say, yeah, if life gives you lemons, then look at it positively and make lemon juice. So the question is how can we pick these smaller tasks? And as we know, for example, from parallelizing and SAT solving, this is not that easy because these problems are usually not easy to split. So if you split them, then there is quite a big communication overhead, which makes the parallelization kind of useless. So it's important to actually look at choosing really independent tasks, because then it can be really efficient. And this is the approach that we looked in this work. So different strategies for exploiting parallelism is so there is one called a strategy competition, which we know from portfolio solvers that were quite successful at SMT competitions and also software competition to a certain degree. That you use the same tool with different settings on the same tasks, and in the task is bug finding. So the first solver that returns a counterexample wins, and then you can abort all the other tasks. So this is one way of parallelizing, which was highly successful. And there was a paper actually from 2008 from Holtzman and others, where they suggest, yeah, we should actually exploit the large number of cores and clusters, etc., to speed up verification and model checking in particular. So in this work, we looked at something different called task competition. So we use the same tool with the same settings, but on different tasks. And as I said before, it's important here to that these tasks are truly independent, so that the approach doesn't suffer from a communication overhead. So how can we partition that? So there, so Maduka and myself had a work a couple of years ago where we looked into compositional techniques for refutation, and we wrote down a small taxonomy of compositional approaches to verification. And the general scheme that we follow there is, so you, if you want to parallelize solving a problem, then you need a pair of operators, a decomposition operator and a composition operator. And you apply the decomposition operator to split it into subproblems, then apply your algorithm that performs verification, refutation, whatever, and then use the composition operator to assemble the results into the final result. And of course, you can apply that recursively, this scheme also inside the algorithm. So, and then we identify two different ways of, or two different categories of such composition operators. So one is that we called horizontal or hierarchical decomposition. So essentially that one follows the components of the system. So this is the classical way how you do rely guarantee reasoning. So you look at a component, prove that this component satisfies its specified contract, and then you use these results in proving the contract of the component that uses these other components. So this is what we usually do for verification. It's not that easy for refutation because the execution traces are somehow cross-cutting to these components, and usually need execution traces to prove reachability of a bug. And yeah, so this turned out to be not that easy for refutation. Whereas if you look at what we call vertical decomposition, that one essentially partitions the sets of execution traces. And so common approaches for the testing or pathwise symbolic execution follow that approach. So this is very suitable for doing refutation. It's slightly more difficult for verification because, of course, you have an explosion of these execution traces. You have to pick your partitions in a way that you don't suffer from this explosion. So in this work, we exploited exactly that. So we do this vertical decomposition. And the advantage of that is that these are actually independent results in independent tasks. So in comparison to this decomposition, you have tasks that are dependent on each other. You have to first solve that, then you have to solve that, you have to solve that, and only then you can solve that. So you have a coupling between the tasks, which is avoided if you do this vertical decomposition. So by the way, if you have any questions, please just interrupt me. Yeah, so this is what we are doing in this work. So how do we apply this idea to concurrent programs? So if you think about a set of interleavings of thread.
Peter, I have a question. So has that work, I mean, this vertical decomposition, can you give some examples in sequential code verification where this decomposition, vertical decomposition has been successfully used? I mean, is Ultimate Atomizer one?
I'm not sure Atomizer is doing that.
Has there been any?
So for example, CLI does that to a certain degree. So CLI does pathwise symbolic execution. So it actually, because it's not that, it doesn't paralyze it, but essentially follows path down and then follows the next path down. Because it doesn't do it in that clean way as it is depicted here, but it's kind of that idea.
Yeah, but I thought the Ultimate Atomizer kind of decomposes the problem on traces into separate things. I thought that's the comparison that I intuition that I was thinking. Maybe not.
Mm-hmm. Yeah, I haven't thought about how Ultimate could be categorized here.
Okay.
Yeah. So with all categorizations like this one, they're always the extreme cases, but then in practice, it might not be. Yeah, there might be combinations of different approaches within a single.
I have a question. This is Ravindra. So this sometime back, I saw this CBMC path, which tried to do path by path. Can CBMC path, can it do this kind of vertical solving? I mean,
yeah,
right
this
now
is kind of what it's
CBMC
doing.
does.
Yeah. So more generally, if slicing is exactly that. If you think about you have some goal, and then you slice your program with respect to that goal, that gives you such a vertical slice of the program. So all these sorts of techniques fall into this category here, which give you independent tasks that you could parallelize.
Okay, thanks.
So coming back to the problem of concurrent programs and how we split these interleavings. So we denote the set of interleavings IKP here. So the K here, so eventually we are going to use our CSEC for solving these independent tasks. And CSEC uses context bounding. So it looks at executions of these concurrent programs that have at most K context switches. So essentially we have a finite set of interleavings because we bound the number of possible context switches. And P is the program that we are going to analyze. And yeah, so we want to split the set of interleavings into subsets that can be analyzed independently. So if you look at different sets of interleavings like this, so this is what we want to obtain. The question is now how we can define these subsets.
So is this only for bounded unwinding? So
yes. So so what we are going to use in the end is bounded model checking plus context bounded sequentialization of this multi-thread.
Okay.
So everything is bounded. Yeah, so what we do is we derive program variants that we call P data here, that only allows context switches in subsets of statements. We call these subsets of statements tiles. And we construct these tiles in a way that we essentially cover all the interleavings of the original program. So we're not losing any behaviors, but we split the behaviors into subsets whose union gives us the original behaviors. So for example, here, this will be example of tiles. They are subsets of statements, and we only allow context switches from within a tile to another statement. Whereas if I'm outside this selected tile, I have to execute sequentially. So I'm explaining in detail how this is going to happen. But this is essentially the idea. So we're restricting the behaviors of these programs by restricting the places in which they are allowed to context switch. And then we enumerate these different selections of tiles in a way that we cover all the original behaviors.
So the new there, in the previous slides, that funny looking character it's ranging over what? That funny looking V.
The data here. This is ranging over the different different selection of tiles. So you see so you have 3 different selections here. So here we pick the first 2 statements here, the first 2 statements here. And context switches are only allowed out of these statements. Same here. Yeah? we pick these and this. And of course, we have to enumerate all the combinations of them. So there's still an exponential explosion there. But as you will see, there is nowadays we have a handle to make a trade-off. I'm going to explain this on the next slides. Okay, so no problem. Good. So just as a reminder how this context-bounded sequentialization works. So we consider that we have multi-threaded programs with n threads plus the main thread. So this is a fixed number, so it's not parametric in n, so it's a fixed number n. And we have a bound k on the number of context switches that we allow. And then we use a round-robin scheduler to construct a sequential program. So we include the scheduler into the program to make the concurrent program sequential, but with but in a way that it allows all possible interleavings up to k context switches. So this is what CSEC is doing. Yeah. And so one of the main motivations behind it is of bounding context switches is that most bugs, it has been observed that most bugs can be found with very few context switches. This was observed first in 2007, right?
So Peter, here in each round there seem to be n context switches, right?
So you need to allow so the gray path here is the sequential program essentially that we construct. So now in each round, so we arrange the execution of the different threads in a round-robin schedule. So you first go to main, then to T1, etc. So now context switches. So each round you allow essentially.
So these TIs are the threads.
The T's are the threads, exactly. Yes.
Okay.
So in each round we allow one context switch by fixing the way to do this is you have to introduce non-determinism in the sequential program to pick where the context switches happen.
Mm-hmm. No,
so in the first round, for example, you could first execute T0 and then jump to T2. And then you have to simulate that there is, for example, a context switch from T2 to T3. Mm-hmm. This can happen in the same round, or you can jump into, yeah. Sorry, let me start again. So in the first round, for example, you could have a context switch from T0 to T2. Yeah? And then, for example, you want to have a context switch to T1. That context switch can't happen in the same round. So you have to switch to the next round to have a context switch from T2 to T1 because it's round robin. Mm-hmm. So, and that way, the number of rounds limits the number of context switches.
Okay, but in the first round itself, I could have n switches, right?
You could have n switches in theory, okay. Yeah. But you could even restrict it and say, okay, if you have I'm actually not sure how CSEC is doing that, whether it restricts that you can really have only one switch per round, or you can have multiple ones. I'm actually not sure. Yeah, but using this construction, we can limit the number of context switches, but still have all the behaviors that can happen with this limited number of context switches. So this is nothing new. This is what CSEC is doing.
Sorry,
So-
Peter, question. Sorry, a question.
Yes.
So, will you be comparing with bounded partial order reduction? How this is different? Like, since you have
We're not. Yeah, we are. So this is not taking into account any partial order reductions. No, this is just a. Yeah, so that this doesn't look at.
No. My question is
how to reduce now.
no. How different is it from partial order reduction? Like, since you have.
It's completely
referred-
orthogonal. It's completely
see.
orthogonal.
I see. Okay. Okay. Thanks.
Yeah. So, so another problem that we have when defining these tiles is that there's still loops in the programs. So there might be call flow that goes backwards, and this makes it difficult to define such tiles. So what we do is that we also bound the loop unwindings upfront. So the bounded multi-checker that we would use in the end would do this anyway, but it makes it easier for us to define a tiling if we unwind the loops upfront. So what we have then is essentially we have a bounded number of threads, and with a bounded number of statements, and all the counterflow just goes forwards. So in this setting now we can define what a tile is, and we say tile is a contiguous subset of visible statements. So visible statements are all statements that can be observed by other threads. Like all the accesses to shared memory are visible statements. So there are many ways how we could define such tiles, and we haven't really explored that what could be advantages there. So we just picked so the simplest possible thing. We just use windows of statements with the same size. For example, let's pick sizes 2, and then we just pick statements that are all block of statement of the same size, visible statements that have actually can be observed in the concurrent execution. So this is very easy to do. There could be other tilings that are more advantageous. We don't know. So once we have done defined these groups of statements that we call tiles, we now need to select which tiles, or in which tiles we actually allow context switches, because we want to restrict these context switches from happening outside the selected tiles. So we call a set selection essentially a subset of set tiles per thread. So here you see a 2 selection. So we're picking 2 tiles from each thread. And we allow context switches only from those tiles that are selected, whereas there can't be any context switches from the tiles that have not been selected. So in that way, you restrict the context switches. So for example, here we allow these kind of executions, whereas outside the tile, there can't be any context switch. You have to execute within the thread until you reach the next tile, and then you can switch out again. So this is the idea. Yeah? And so each selection, so in this case, selecting 2 tiles from each thread, is called a reduced interleaving instance, because it picks a subset of possible interleavings. And this is a task that we are going to execute. Of course, we have to enumerate all these different set selections. So another would be where we pick this and this, and this and this, and this and this, and this one and this one. Would be another one. Of course, they are exponentially many. Yeah? I'm going to show you later how we solve that problem. So why is this these selections complete? And how do we have to pick them so that it is complete? So the interesting thing is that so we are bounding context switches to k, at most k. And the interesting observation here is that when context switches are bounded to k, then within a thread, you only have to pick k over 2 tiles, because once you can only switch out from one thread k over 2 times at most. So we don't have to select more tiles than k over 2. So this gives us an upper bound on the number of tiles that we have to select in each thread. And so if we select more than k over 2 or tiles, then we can cover all the existing all the interleavings of the original program. So as I said, the number of these different selections, these debtors.
Can I ask a question?
Yes.
So the ordering is still maintained, is it? I mean, you can only switch from T0 to T1, T1 to T2, and so on.
Yes. So the ordering is maintained. Yes. Yeah.
So, but then how do you take care of something where you switch from T0 to Tn and then back to T1?
Yeah. So this is in the encoding that you can actually you can jump from T0 to T2, for example. Yeah.
Oh, okay, you can do that. Okay.
Yes, you can go that way. This is already the case in the original CSEC encoding.
Mm-hmm.
This is just simplified.
So I have another naive question. How do we know that from one tile, when you jump to the other tile, that is a feasible execution? Because the execution of the other thread may not reach there, right?
No, you're not jumping from one tile to another. So the tiles only tell you that you can only have a context switch out of a selected tile.
Okay.
But you can still jump to a statement that is outside a tile in another thread.
I guess Ravindra's question was, is it a feasible jump? I mean, can you?
Yeah, the jump.
Yeah, so the feasibility of the jumps is already constrained by the original. Going back to by the original construction here. So this only allows feasible jumps.
I see.
And we are essentially only restricting the jumps that are already specified here. So we're never introducing infeasible jumps because they are not there in the first place.
In the sequentializer construction itself will take care of that.
Yes,
feasible
exactly.
jump. Okay.
We are only essentially reducing the number of jumps in the sequential from the sequentialization.
Okay.
I think also that not every every interleaving may be a feasible execution, right? Because they have shared variables and you have if statements, and so you might switch to something from T0 to T1, but that may not be T1 may not be enabled, that statement.
Yes, but then you can't switch from T0 to T1. So the encoding of the sequentialization already takes care of that.
Okay. Okay, but maybe if, for example, if you had locks or something, then you might not be able to always switch, right? I mean,
yes, it could be that you jump from T0 to the log statement in T2, and then have just to check, the log is still, you're still not unlocked. You have to jump to another thread immediately. Yeah, so
Right,
this can
okay.
happen, of course.
Even
But
if
this
that's
is
not a
all
tile, right?
as part of the sequentialization.
What if that is not a tile?
This is a good question, yeah. I don't know whether we take care of that. I think we should.
Maybe
It's
see
a
whether
good
it's a
question.
feasible jump.
Yeah.
Anyway, you have the global state, I guess, and you can check whether it makes sense to jump
Yes.
to that.
Yeah.
State.
Yeah. Good. So what we still have to do is we have to enumerate all these selections of two tiles in these threads. And what we do is we actually we sample. So we take a random selection and use that one for the first set of tasks that we execute, and then take another random selection as well. I'll explain this in a second. So, so we've implemented this in a tool called Very Smart, and you can find it on the website, the CSEC website. So it's for multi-thread C programs, and so where is this even useful? Because it was very difficult to find a large number of benchmarks for that, so in the end we only found 2 benchmarks where this is actually really useful, and so we need, for this to be useful, you need rare concurrency bugs. So which means you have a large number of interleavings, and only a few of these interleavings lead to the bug. So this is the definition of a rare bug. So we use it for bug finding. So this is obviously not, so everything is bounded. So this is not for useful for verification. And the properties that we use are reachability properties like assertion failures, out of bound problems, etc. We're using the CSEC approach of a source-to-source translation for implementing these tilings, and then run it on a cluster. So, so what are the steps that we do in the tool?
Yeah.
So
Peter, I have a question.
Yes.
So, given that, what do you parallelize here? I kind of missed. You started out by saying you were going to parallelize different tasks. Which are the tasks that you parallelize?
So the tasks that we parallelize are these. So where is it? These P data. So these are the reduced, the restrictions of the programs where we have reduced the number of interleavings by this tile construction. So one selection of these tiles, like that one that you see here.
So each selection combination of the...
If selection combination is a P data, exactly.
So that can be done independently of the other combination, although there could be exponentially many such combinations.
Exactly.
And can you explain what this intuition of why you need to only, this is just the K by 2 is for what? What is that? How does that?
So this is for how many tiles do I have to select in each thread.
Why is that?
The reasoning here is, since we have bounded already the number of context switches, we only have to select K over 2 in each thread. Because in order to have, so you have to switch out of a thread, then you have to switch into it again, and you have to switch out again. So you're at most K over 2 is sufficient to cover all the behaviors.
I see. Others will be symmetric or something. The others will be symmetric? Or what?
Yeah, so if you just have a problem with two threads, and you have the number of context switches is bounded to k, then you can only jump out of each of the threads at most k over 2 times, because you have essentially k over 2 context switches out of the first thread and k over 2 context switches out of the second thread. You can't have more than that, because overall it's bounded to k.
Yeah.
Good. So what are the different steps that we do in the tool? So first we inline and unwind everything. Then we we identify what are the visible statements. So this essentially identifies the basic granularity of statements that is used for the tiling. And then we perform the instrumentation, so the construction that CSEC uses. And the additional thing is that we can also control now the context switches. So we can essentially select which context switches we want to enable and which we want to disable. And that way we can construct these different P data programs. And so this enabling and disabling of these context switches is done in the split module. And so the parameter here is the size of the tiles. And it constructs for a given size of tiles, it picks a certain number of variants randomly. And these are then assigned to each node in the cluster and solved. If the first one that finishes with finding a bug, then we are done. If all of them run into a timeout, then we go back and pick the next n randomly selected variants, p datas, and run again until we find the bug. So eventually we would cover all the possible p datas, but unlikely to happen because the number of these is very large. What you've seen is that we find actually the bug with a relatively small number of instances that we select. So why does this work? We're performing a trade-off here. So we have each p data we reduce the number of interleavings, which makes it easier for the verification tool to analyze that instance. So each instance is smaller and easier to solve for the verification problem. On the other hand, the bugs that we're looking at are very rare. So if the instances has only very few interleavings, the probability that one particular instance contains the bug or exhibits the bug is relatively low. So most of the instances will actually just run into the timeout. But those instances that exhibit the bug will find the bug very quickly because the instance is small. So there are many instances that just run into the timeout. So the overall CPU consumption is high, but the vault log time to find the bug is low. This is the idea why this is the performance gain. So you have many instances in parallel, and the hope is that some of these instances will finish very quickly and find the bug. And I'll show you now what the experimental emulation has shown. So we found two benchmarks with really rare bugs on log-free data structures. One of them is the elimination stack benchmark. So that one we analyzed under sequential composition, sequential consistency. There are linearizability assertions in that benchmark. And so without the approach that I have showed you here, lazy CSEC can actually find the bug, but it needs 13 hours to find it. And yeah, back then when we did the experience, there was no other tool that could solve it. I don't know whether this is changed in the meanwhile. But this is a really hard benchmark that takes a very long time to solve. And another one, also a log-free stack implementation. So that one has even a context bound of 5, which is extremely high. So that was published in a Microsoft forum. So we analyzed it for sequential consistency, PSO and TSO, and there are some interesting insights about this weak memory. Using weak memory semantics in this for these benchmarks. So also this takes really long, 7 hours. Also needs quite a lot of memory. So what are the results? So essentially, running lazy CSEC on the entire benchmark, so essentially picking all the interleavings at once, takes 13 hours. So we then tried what happens if we pick 3,000 interleavings, so single interleavings, and we use CVMC as the backend. And how does CVMC cope with that? So this gives us some idea about what is the sequential complexity of the benchmark. And we see that is relatively low, so CVMC needs a bit more than a minute. So sequentially, this benchmark is relatively simple, but the complexity comes from the interleavings. And picking 3,000 interleavings, we didn't find the bug. So it's very unlikely by just picking random interleavings to find that bug. So now with the tiling approach, we looked at 3 different tile sizes. So tile size 12, 14, and 18. And then what you see here is for what is the minimal maximum average time of the different tasks that we executed. So what you see here
is 5 here?
Pardon?
The K is 5?
K is... Sorry. K is... K should be 3 here. It's 2 rounds means K3, I think. Yeah.
Okay.
So the other one in K, for the safe stack, K is 5. Yeah.
Okay.
Yeah. So the first thing that we see here is that the fastest instances that exhibit the bug are extremely fast. So 35 seconds as compared to 13 hours. The slowest ones are still 10 times faster than solving the entire benchmark in a single run. And on average, the speed up is times 14. Yeah? So the other thing is, so with larger tile sizes, of course, it becomes slower because we have more interleavings in each instance. Still, the speed up is 10 times here. Memory assumption goes down. And so for this benchmark here, it's interesting to see there's a really, the bug is actually not that rare for when we use the tiling approach. Because here we have in 40% of the selected tiles actually exhibit the bug. And the percentage increases the larger the tiles because there are more behaviors in a single instance. So if you, this might still be confusing, but so you can think about this is a trade-off between, so if you're, for example, you perform fuzzing on that benchmark, which essentially selects a single interleaving, This would be on the very left-hand side here. So you have instances with the bug percentage will be very, very low. Then the more you increase the tile size, the more behaviors, the more interleavings are in each instance. And on the other end, you essentially have the instance where you select all the interleavings, which is this one here, that takes 13 hours. So this tiling mechanism is essentially a trade-off to find to pick select interleavings, a certain amount of interleavings where the benchmark is easy to solve, but there's still a high percentage of high probability to find the bug in the instance. Sorry. Yeah, I think there's still time to go. So, so this graph actually shows you.
And in the previous slide,
yes,
have you? I mean, you've increased the size of the tiles. I mean, these times that you have shown with parallel execution, have you executed? I mean, have you explored all possible combinations of
No.
tiles or not? No. So,
No.
which means then you can't compare it to, I guess, lazy CSEC, because they're for a particular bound in the context which it explores all interleavings, no?
Yes, but this is the point. By selecting, so you want to choose a tile size that contains a sufficient number of interleavings that exhibit the bug, but at the same time reduce the time for the model checker to solve that instance fast. So this is not about, it's really just about reducing the wall time to find the bug.
So which means that here the instances with bug, you say 69, it has only found 70% of the bug, is it?
No, there is only one bug. It says in 70% of all instances we find the bug.
Okay, go ahead. I mean, yeah.
So instances means one particular tile selection?
Yes, so one instance is one P theta. Yeah, so this graph shows you now the relationship between the number of instances, P theta, or this number of parallel instances that you have to execute, versus the bug finding time. So essentially the wall time for finding the bug. And so we did this estimation here. If you want to find a bug with 99% probability, then you pick only five instances, you can find the bug in less than 500 seconds for this benchmark. So if you pick more instances, you can reduce the time even further. So the fastest one was 35 seconds. If you pick enough instances and you're lucky to hit the one that only takes 35 seconds, you have solved the benchmark in 35 seconds instead of 13 hours. So let's have a look at the other examples, which has slightly different trade-offs. So the safe stake example, we see that this bug is much rarer. So we have again 3 different tile sizes here, but here the instances that contain actually the bug is much slower, much smaller here, only 1% or 2%. And tile size 20, it's 10%. So this is a extremely rare bug. Still have a speed up of on average of 20 times. So let's look at this picture again. So here, So this point here is finding about 95% probability. We need to look at 32 instances. And so if you look at 32 instances, then with 99%, 95% probability, we find the bug in 1300 seconds. Now I think this point here is for 99% probability. You have to pick probably, I don't know, 60 or so. So this is with tile size 20. So if you pick a smaller tile size, then so smaller tile size means one instance has a lower probability of containing, exhibiting the bug. So you have to choose more instances. So to get again at 95%, here you have to choose roughly 300 instances. So these are the trade-offs that become apparent now. And you see that smaller tile size means you have to pick more instances, but since the instances are smaller, you might find the bug faster. Yeah, so we also looked at PSO and TSO, and the interesting thing, or maybe unsurprising, is that it becomes easier because there are more behaviors. So there are more, the fraction of, the probability of finding a bug in an instance is higher. So PSO is actually, yeah, in that sense, easier than sequential consistency. Yeah, so these 4,800 seconds is for the all interleavings. If we use the approach with tiling, we still get some speed up. Yeah, like we can find it in with, I don't know, 100 instances. We can find it in half the time. So. Good. So what I showed you is a task, a strategy approach to parallelizing the bug finding in concurrent programs. And so we can exploit the availability of many cores to solve tasks independently. And this allows us to handle these extremely hard verification problems. And it was also surprising to us that actually the number of cores that you need to find the bug with relatively high probability is relatively small. So we used CVMC as a backend. So this the approach is completely independent of the backends that you can use. You use anything, yeah. You can use CLI, you can use a fuzzer or whatever. Yeah? What we also haven't explored is different tiling style. So we have just picked the simplest one, but it could be that other tilings that are more informed by data flow or whatever can give even better results. We haven't explored that. And a third thing that we have looked into is if we could rule out safe instances faster. So currently the approach essentially on the safe instances, we always run into a timeout. Because it's the usual problem with SAT problems that the unsatisfiable ones are usually harder than the satisfiable ones. So we always run into the timeout when an instance is safe. So if we could apply over approximations, so doing some static analysis to rule out safe instances, that this could further speed up the verification. Good. That's everything I have. Are there any further questions?
By fast over approximations, you mean quick way to compute the over approximation. What do you mean by fast over approximations?
I can hardly hear you.
Yeah, what do you mean by fast over approximations? Quick way of computing the over approximation? What do you mean by fast?
Yeah, so if we can determine essentially if we can prove that the bug doesn't occur in an instance fast, then essentially the core becomes free to take on the next task. But of course, this only helps when they proving that the instance is safe is faster than the timeout that we have. So currently, the approach is we set a timeout of 1.5 or 2 hours, and if we run into the timeout, then we say, okay, we don't know anything about that instance. Let's pick the next task. But yeah, of course, this is a huge waste of CPU time, because each instance that doesn't exhibit the bug, essentially we run up to the timeout.
So you need
so if
the
we had something that's faster to tell us that instance is actually safe, then this would free up the core, and it could start tackling the next task.
Yes, but yeah. Sometimes, so you have to get the kind of over approximation over which it should be fast to prove.
Exactly.
It should be fast to prove. Huh?
Yeah.
Can invariance help here?
Possibly, yeah. Yeah. So one advantage with the since now have reduced the number of interleavings, it should also become easier for a static analyzer to analyze that, because there are fewer joins in that instance where it could lose precision. Right? So in principle, it should also be favorable for the static analyzer to handle these instances.
So Peter, you talked about these the tiling. I was going to ask if there is a way to learn what is a good tile, but you mentioned that you're looking at rare bugs. So I believe that learning then would be difficult. If you're looking at rare bugs, then and a machine learning algorithm would not perhaps be able to tell us what is a good task or what is a good tile to start with. I mean, what is a good selection of tiles to start with? So are there other ways of identifying what could be a good selection of tiles? Have you looked at that?
No. So this is one of the things we haven't really explored much. So what we did is essentially we started with a tile size. I think it was 10. And then we looked what the results were for 8 and 12. And then, seems we should actually increase the tile size further, its advantages. So we did that, and then we explored a bit the space of tile sizes that are could be useful. Yeah? But of course, this is a very ad hoc approach.
Yeah. So one thing is certainly the tile size. The other thing is also for a given size, what is the selection that you begin with first, and then how do you choose the next selection and so on?
This is true. Yeah, this is purely random at the moment.
Yeah.
So there is
Yeah. So what do you think there are techniques that can help there? Learning, of course, perhaps would not be very helpful because you're looking at programs where bugs are extremely rare.
Yeah, I don't know. So learning from data is difficult in that case because you don't have that much data. what obvious candidate is, of course, you look at data flow or synchronization patterns and things like that to inform your tile selection. This could maybe help. I don't know. We haven't. Yeah. Sure. There's certainly work to do in this direction.
Yeah.
So, Peter, does it? Can you use some of these ideas to actually do verification parallelly?
I
mean, not bounded verification, but actual.
Yeah.
Use induction. I don't know what kind of induction.
We honestly haven't thought about that at all. Yeah, whether a similar approach could be used for that.
Because if you can still prove that each of those with each instance is, let's say, safe.
Yes.
You have a proof.
Exactly. Yeah. So if you can prove that each instance is safe, then you have proven that the entire thing is safe. Yes. Yeah.
No, but that is still only for that bound, no? What do you mean?
Yeah, so assuming you lift all the bounds.
Yeah, but how do you lift all the bounds? Yeah.
Yeah, this is a good question, yeah. Because we have, so the bounds even play a role in the tiling approach that we take. Because in order to define the tiling, we currently have to unwind the loops. Otherwise, our tiling definition doesn't even work.
They have a layer of IC3 on top of this?
Yeah, possibly. Don't know.
Yeah, but you don't need to bound anything, right? I mean, in principle, you could define a tile as a subset of the statements in each thread.
Yeah, you have to.
No, but you still have the bounded context switches, no? So how will you?
No, you don't need to.
That only works for the bound. I mean, that the reason he's able to get that k/2 is because he's bounding the context switches. Now, if you want to prove.
Yes, this is also correct. Yeah. So right. You have to think how you can actually put a bound on the selection so that you still cover all the behaviors. Yeah. So this also gets slightly more complex. Yeah. So you need a different argument for selecting, and this might not be. Might be parametric in the number of threads, number of context switches, etc., number of loop unwindings.
Yeah, but the main thing is that you kind of lose the structure of the program when you do this. I mean, yes. Let's say you had some way of reasoning about, I don't know, maybe concurrent. I mean, essentially, it's still concurrent threads, and you may have some ways that work well in structured programs, but I mean, like rely guarantee. But if you have these styles and you kind of lose the structure of the program,
the reason why we decided to completely remove the structure of the program is because it was much easier to define these tiles.
So is this available for experimentation, this tool?
Yes. Yeah. So it's available on. Where did I put the link? Yeah. It's on. This is the CSEC website.
Oh, okay.
This published work?
This was published at ASE 2017.
ASE.
Automated software engineering.
ASE what year?
2017.
So these tilings are so the selection of tiles, they don't intersect on, as in they are disjoint for interleavings, or there are interleavings that are common to more than one. There are interleavings, in fact, that are common to more than one selection of tiles.
In principle, they shouldn't, because the tiles are disjoint, and also the selections are disjoint. So in principle, each interleaving should only be part of one selection.
So there was a point where you mentioned that 70% of the cases there was a bug. So if there's only one bug.
Yes, but it doesn't mean that. So the problem is the reason why you do partial order reduction is because there are many interleavings that are equivalent.
Okay. Yeah.
So there are many interleavings that exhibit the same bug.
Okay. Yeah, so if there are no further questions, then yeah, so let's thank the speaker. Yeah, thanks a lot, Peter, for your wonderful talk. And yeah, so that concludes things from here. We'll meet again next month, and the details of the next talk will be put up on the website very soon. Yeah, thanks a lot, Peter.
Thanks, Peter.
Thank you.
Shankar. Yeah.
Right.
Thank you.